Welcome to Dr. Paul Jones's Fun with Line Formalism. I've drawn a molecule, a completely made up hypothetical molecule. I have no idea if anybody's ever made this molecule or not. But I'm going to invite you to answer some questions about it. So, first of all, take a good look at it. It's line formalism. So the ends of the lines represent carbon atoms. Any intersection of lines represent carbon atoms. We assume that the valence of the carbon is made up of hydrogen for any bonds not shown. We have to explicitly write in heteroatoms, that is, atoms that aren't carbon or hydrogen. There is one hydrogen missing from this molecule that does need to be written in. So hit pause, take a look at it, hit pause, and write down, actually before you do anything, write the molecule down on a piece of paper. I know you guys like to just watch this stuff. Write this molecule down on a piece of paper. Now, hit pause and put in the hydrogen that's missing. Okay, you back? We have to show any hydrogen that's on a heteroatom. You have to explicitly draw that in. You don't have to draw the bond, you could just write an H below it, but you have to show it somehow. All right, now, again, hit pause and write in any lone pairs that exist in this molecule. We don't normally draw in the lone pairs, but it's important to know they're there. So go ahead and write those in. All right, you're back. I'm going to write those in green. So oxygen needs a full octet, right? Every atom needs a full octet, I suppose. So oxygen has 2 bonds, neutral oxygen has 2 bonds, and 2 lone pairs. Again, you have to explicitly write in any charge, and I haven't done that. Nitrogen, to be neutral, 3 bonds and a lone pair. Sulfur is right below oxygen on the periodic table, so when it has 2 bonds, it has 2 bonds and 2 lone pairs. Sulfur and chlorine that are shown here can expand their octet. They're third row elements. They have available a d shell in the valence shell, a d orbital, and d orbitals in the valence shell. And so they can expand their octet. They can have more than 8 electrons. They don't always. Very often, especially in organic molecules, they obey the octet rule. So a sulfur there with 2 lone pairs. The chlorine then has one covalent bond, 3 lone pairs, and is neutral. So you can go through and calculate formal charges. Chlorine, for example, has 7 valence electrons, 7 minus 6 lone pair, minus half of 2 shared is 0. Sulfur works out just like oxygen. Everything's neutral here. All right. So now, hit pause again and write in all the hydrogen atoms. I'm going to put those in blue. Okay, you back? So at the end of the line, we're going to have what we call methyl groups. So a CH3 is a methyl group. I'm going to check that I'm on the... You guys don't know this, and I'll go ahead and tell you. I filmed these several times, and the first few videos I wrote on the board and cut my head off and cut off most of the molecules I was working on. So okay, end of the line is going to be a methyl group, which is a CH3, and so write in the 3 H's there, H, H, H. That carbon, 3 bonds are shown. 4 bonds minus 3 bonds, there's 1 bond left. Hydrogen atom there. All right, nitrogen. This carbon has 4 bonds shown. Carbon gets 4 bonds, doesn't get more than 4 bonds. Carbon with more than 4 bonds would violate the octet rule. So if 4 bonds are shown, it's done, there's nothing else on it. Same with this carbon. 1 bond, 2 bonds, 3 bonds, 4 bonds. So 3 things, but 4 bonds, so it has no hydrogens. This carbon has 1, 2, 3 bonds shown, so it's got another hydrogen. I'm going to go ahead and fill this in. You can work that out. Check your answers. This carbon has 4 bonds. Bond here, 1, 2, 3 more. So 1, 2, 3, 4 bonds. Same for this carbon, 1, 2, 3, 4. No hydrogens on either of those. 2 on this one. Okay, very good. So you should have this. I think I got everything there. Okay, now I want you to figure out the molecular formula and then the number of unsaturations in the molecule. So go ahead and hit pause and do that. Okay, if you're back, let's do carbon first. 1, 2, 3, 4, plus 6 for the ring, 10, 11, 12, 13, 14, 15. C15. Alkynes, carbon-carbon triple bonds, tend to trip people up. This is not one atom. This is a carbon triple bonded to another carbon. All right, so then there's single bonds coming off. sp hybridization, they're linear. All right, now the number of hydrogens. This gets a little tricky, and honestly, in one take, I screwed this up really badly. So let's count the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There's just a very odd sound in here, sorry. So C15H18. And now you put the other elements in. You do this in alphabetical order. There's a chlorine, there's a nitrogen, there's an oxygen, and there's a sulfur. There's just one of each, so you just write the letter. All right, now number of unsaturations. And again, you can do this with the equation I provided in class. Units of unsaturation equals 2 times 15 plus 2 minus the number of hydrogens minus 18. Is that the camera? There's a really weird sound in my office. Sorry. So 2 times the number of carbons plus 2 minus the number of hydrogens minus the number of halogens, which is 1 for chlorine, plus the number of nitrogens, 1 for the nitrogen. Oxygen, sulfur don't get involved, right? 2 bonds, they're just a linker between 2 groups. And then you're going to divide this by 2. 30 plus 2 is 32, minus 18 is 14, minus 1 is 13, plus 1 is 14. You could probably just figure out to cancel that. So this is going to be 14 divided by 2. That's 7, 2 touchdowns. I learned math doing football, so you should have 7 unsaturations. Is that accurate? Remember, a ring is an unsaturation, a pi bond is an unsaturation. 1 pi bond, 2 pi bonds, 3, 4, 5, 6. Remember, a carbon-carbon triple bond is 2 pi bonds, sigma and 2 pi bonds. So 1, 2, 3, 4, 5, 6. 6 pi bonds, 1 ring. 7 units of unsaturation. So the formula works out. You could just do this at a glance. I gave you a structure so you didn't have to do this, but I thought we'd work through it. All right, I'm going to erase this. I'm going to look at the camera. I'm going to erase the units of unsaturation and ask you a couple of other questions. Camera seems fine. All right, get this down if you want it. I'm going to obliterate the H's. I'm going to take off the lone pairs. Okay, so now I want you to put a star, an asterisk, by any sp2 carbon. Okay, so hit pause. You got your molecule. You might want to redraw it. It's getting cluttered. Put a star next to any sp2 carbon. All right, I'm going to do that. These, no pi bonds, no double bonds. So they're not sp2, they're sp3. So any carbon that doesn't have a double bond or a triple bond or a pi bond of some sort is sp3. 1 triple bond. There are 3 things bonded to it. It's trigonal planar. It's flat. Has a bond angle of 120 degrees. You should know that. So that's going to be an sp2 carbon. This carbon, 1 double bond, 3 things bonded to it. That's sp2. In fact, all the carbons in this ring are sp2. So star equals sp2. All right, now circle any sp carbons, sp hybridization. All right, are you back? So sp carbons have 2 pi bonds, 2 sigma bonds, 2 pi bonds. The only 2 are these 2, so that one there and that one there. You'll usually find sp carbons bonded to one another in a triple bond. So those are sp. All right, now put a triangle around any sp3 carbons. Okay, again, single bond, no pi bonds. All three of those are sp3 hybridized. They're tetrahedral, have a bond angle of 109.5 degrees. These are already taken care of. Two things here, right? If you draw those in, two H's, no pi bonds. So that's sp3. The same goes for that carbon, and the same goes for that carbon. Don't forget that guy out there. All right, that's the hybridization of all those. All right, so I hope this explains a little bit about line formalism. Go ahead and you should do the examples in the book. Rewatch this if you need to. And again, please come in and ask me any questions if you have. All right, thanks.